Hello everyone, I'm Zhen. I will be presenting our learning-based approach for 3D-aware facial landmark detection. We propose a novel 3D-aware facial landmark detection algorithm. Specifically, we propose an approach to synthetically generate a high-quality multi-view dataset with 3D consistent landmark annotation. Here is an example from the dataset. Moreover, we propose multi-view consistency losses to fine-tune an existing landmark detection network on the newly introduced dataset. Our approach can be plugged into any learning-based facial landmark algorithm. As seen, our refined version of DAD 3DNet produces facial landmarks that are better aligned with key features of the individual. Accurate and precise facial landmark plays a significant role in computer vision and graphics applications, such as face morphing, facial reenactments, head pose estimation, among others. However, existing facial landmark detection approaches detect 3D or 2D facial landmarks that are inconsistent with the 3D geometry. This is mainly because the current in the wide training data are manually annotated, and such annotations are not multi-view consistent. Now, let me explain why manual annotation is problematic. First, annotating faces in extreme poses require guessing the positions of invisible landmarks, which is inaccurate. Moreover, even the visible landmarks are not multi-view consistent. This can be clearly seen when a flame-fitted mesh is used to project the landmarks onto another view. This inaccuracy and multi-view inconsistency leads to the loss of the semantic meanings associated with landmarks, which will be the key factor to learn an accurate landmark detector. To address this problem, we propose to create a simulated multi-view image dataset with 3D consistent landmark annotation. Specifically, we use a single image along with its 2D landmark and estimated camera parameters as input. We apply EG3D inversion to this image and camera information to generate the corresponding depth map and nerve representation. Using the depth map combined with the camera parameters and the 2D landmark, we employ recasting to obtain the 3D landmark coordinates. By summoning additional cameras, we can project the 3D landmark onto the corresponding views, resulting multi-view 2D landmarks that maintain 3D consistency. Additionally, the sampled cameras can be used to render multi-view images using the nerve representation as input through volume rendering. Our dataset named DAD3D has seen consists of these multi-view images that have been annotated with multi-view consistent landmarks. We use this synthetic data to fine-tune an existing facial landmark detection algorithm. Next, I'm going to discuss our 3D-aware multi-view consistency training. We fine-tune a pre-trained landmark detection network using both the original and our synthetic dataset. We use the original loss when using the original dataset, but propose a multi-view consistency loss, which I will explain in a bit for training examples from our multi-view dataset. The overall loss is the combination of the original loss and the multi-view consistent loss, which is backpropagated to fine-tune the network. Now, let's look at our multi-view loss in detail. We pass n views to the baseline network to obtain predicted landmarks. We then randomly select p predicted landmarks to calculate the canonical 3D landmark. This 3D landmark is projected onto the image planes of the rest of views to obtain their projected landmarks. Next, we calculate losses among the predicted, projected, and ground truth landmarks. Specifically, we formulate the area between the predicted and projected landmarks as self-projection consistency loss, and the distance between the predicted and ground truth landmarks as multi-view landmark loss. The multi-view consistent loss is the combination of these two losses. Now, let's take a look at our results and comparisons against state-of-the-art methods. For quantitative comparisons, we calculate NME of facial landmark detection results on DAD 3D heads, facescape, and multifaces, according to the results of 3D-DFA, 3D-DFA Plus, DAD 3D Net, and DAD 3D Net Plus. It is evident that after refinement, the new models achieve much better results than the baseline models. To visually validate the improvements gained by our approach, we compare the refined method against the baseline method on different datasets. On DAD 3D heads scene, we can observe that the refined method generates results that are better aligned with the identities. Similarly, on the DAD 3D heads, the refined method demonstrates increased accuracy compared to the baseline method. Furthermore, when evaluating our approach on the facescape dataset, we found that the refined methods perform better in detecting landmarks around the eyes and mouth regions. Additionally, on the multiface dataset, the refined method produced more accurate results. Conclusion. We propose a novel 3D-aware multi-view consistency framework and introduce a multi-view dataset simulation pipeline. We present a multi-view consistency loss function and also demonstrate the efficiency and effectiveness of our approach against state-of-the-art methods. Thank you.